Imagine betting like $2 billion on a single rocket launch.
Right, and human lives on top of that.
Exactly. Human lives billions of dollars, and knowing that the only thing keeping this massive machine from just exploding on the pad is, well, it's essentially the exact same foundational high school algebra used to calculate, like a train leaving a station.
It is wild when you actually stop and think about it.
It really is. Because we spend years learning math in these neat, isolated little chapters, you know? You take a test on algebra, you forget it, you move on to calculus, you forget that too.
Yeah, you just dump the information and move to the next silo.
Right. But the real world doesn't operate in isolated chapters, and that is what we're getting into today. Welcome to this deep dive, where we're going to explore a very specific, honestly pretty intense curriculum document we've got in front of us.
Yeah, it's titled Day 33, Engineering Math Toolkit Integration.
Which sounds like a mouthful, but it's actually the final module of a really grueling 33-day Class 12 mathematics engineering track.
And what's fascinating is that rather than handing you just one final equation to memorize for a test, this document demands a massive paradigm shift.
Yeah, it's not about learning a new rule. We're looking at how these completely isolated mathematical frameworks are stitched together to essentially run the modern world.
It really is a fundamental shift from just learning math to actually architecting with it. The mission for us today in this deep dive is to explore the mechanics of that unification.
Right.
We're going to look at how linear, algebra, calculus, and probability are forced to interact within a single computational framework.
And why that even matters, right?
Exactly. Because understanding this pipeline is critical for anyone trying to grasp modern engineering, software architecture, or, simply how the complex systems you interact with every day actually function without collapsing.
Okay, let's unpack this. Because the curriculum frames this entirely around a concept called systems integration.
Yes.
And the core mechanism driving that integration, the thing that makes it work, is something called a boundary condition.
Right, the boundary condition.
So if we are moving away from isolated math engines, how do boundary conditions actually force these completely different disciplines to talk to each other?
Well, a boundary condition in this context is the exact state of a system at the moment one mathematical process ends and another begins.
Like a handoff.
Exactly like a handoff. Think of it as a strict data handoff. You can't just mash algebra and calculus together in a bowl and hope it works.
Right, they don't speak the same language automatically.
No, they don't. The algebra engine processes a specific set of parameters, say spatial coordinates, and its final output becomes the absolute non-negotiable starting constraint for the next step.
The boundary condition.
Yes, the boundary condition for the calculus engine. Calculus cannot run its kinematic formulas until it receives that precise numerical state from the algebra layer.
Okay, so it's a pipeline broken into 3 distinct layers. Let's break down the mechanics of those layers, starting with the first one, which is linear algebra.
Right, matrices and vectors.
Yeah, and the curriculum defines this as the spatial framework and state tracking layer. What does that actually mean in practice?
Well, linear algebra is essentially the geometry of the system. People hear matrix and they just think of a grid of numbers.
Or the movie.
Right, or the movie. But mathematically, it's a mapping of space. If you have an object, the matrix defines its scale, its rotation, its precise coordinates in 3D space at any given, frozen millisecond.
It's taking a snapshot.
Exactly. It establishes the where and the what. But space without movement is static. It's just sitting there.
Right, nothing is happening yet.
So that static state is handed across the boundary condition to the second layer, which is calculus.
Which acts as the kinematic engine.
Yes.
So calculus, and we're talking specifically about derivatives and differential equations here, it takes that frozen spatial data from the matrix and calculates how it changes over time.
Precisely. It calculates velocity, acceleration, the curve of a trajectory.
Because a derivative is, by definition, an instantaneous rate of change.
Right. So if linear algebra tracks the position of an object, calculus looks at that position and dictates where it will be 1 microsecond from now based on whatever forces are acting upon it.
But there's a catch there, right?
There is. Calculus inherently assumes a perfect, frictionless universe where the math always behaves exactly as written on the chalkboard.
Which is definitely not the real world.
Not at all.
Which brings us to the third layer, probability and Bayes' theorem, because the real world is, well, it's incredibly messy.
Well, it's full of noise.
Yeah, you've got wind, friction, temperature fluctuations. So the probability layer acts as this error correction mechanism to manage sensor noise and system uncertainty.
Exactly. So calculus might say an object is moving at exactly 50 meters per second. But the physical sensors tracking that object might be reading, I don't know, 50.2?
Because of atmospheric interference or whatever.
Right. And probability doesn't just throw its hands up and say, well, the sensor is wrong. It uses Bayesian logic to weigh the calculus prediction against the noisy sensor data to determine the most statistically likely reality.
It's finding the truth in the middle. Thinking about this three-part pipeline, spatial framework, kinematic engine, error correction, it perfectly mirrors a modern video game engine.
Oh, that's a great analogy.
Right, because if you are playing a massive 3D open world game, that first layer, the linear algebra, that's the GPU crunching millions of matrices to render the polygons of the mountains, the buildings, and the exact coordinates of your character.
It's building the static architecture of the digital world.
Exactly. And the moment you press the controller to make your character, say, jump off a ledge, the physics engine takes over.
Which is the calculus layer.
Right. The game engine pulls your coordinates from the linear algebra layer, feeds them into a differential equation, and calculates your falling arc, factoring in digital gravity and acceleration.
But then you run into network lag.
Yes. You're playing online, the server drops a packet of data, and suddenly the game doesn't actually know where you are for a split second.
So it relies on the third layer.
Probability, or what developers call netcode prediction. It literally calculates where you probably landed based on your last known trajectory, smoothing out the lag so the illusion of the world doesn't just shatter for the player.
That is exactly how it works. And that underlying structure, static state, rate of change, probabilistic correction, it's universal.
It's everywhere.
It is. The video game analogy is really helpful for visualizing the digital space, but the curriculum immediately forces us to apply this pipeline to highly physical life and death systems.
Right. It moves straight into aerospace engineering.
Yeah, the design of launch vehicles.
Specifically, it talks about a framework called MDO, or multidisciplinary design optimization.
Which is a huge concept in aerospace.
Yeah. So when engineers design a rocket, they are relying on this exact math pipeline to ensure the vehicle actually reaches orbit safely. They use vector algebra to map the 3D orientation and trajectory of the rocket.
Right. The vectors provide this rigid framework of the vehicle's attitude. Its pitch, yaw, and roll relative to the Earth.
Okay, and then differential equations come in to model the thrust and drag over time, because as the rocket burns propellant, its mass physically decreases.
Exactly. And a lighter rocket requires a different thrust profile, which changes its acceleration, which in turn changes the atmospheric drag hitting the nose cone.
It's just a cascading chain of changing variables.
It is. And layered on top of all that is linear programming, which is from day 31 of the curriculum. And that's used to optimize the fuel-to-payload mass ratio.
Because weight is everything.
Right. Every single extra ounce of fuel you add to a rocket requires more fuel to lift that initial fuel.
It's a vicious cycle.
You are constantly brushing up against the boundary of the rocket equation, trying to maximize your payload without running out of propellant a mile short of orbit.
Okay, wait, I'm getting stuck here for a second. If calculus is constantly recalculating the required thrust based on the changing mass, and the linear programming layer is relying on that thrust data to calculate the optimal fuel load, wouldn't the system just freeze up in a paradox?
How do you mean?
Well, how does a computer solve two complex equations that rely on each other's outputs at the exact same time without crashing? It sounds like a snake eating its own tail.
I see what you mean. What's fascinating here is that it doesn't solve them simultaneously.
It doesn't.
No, it relies on a continuous automated feedback loop governed by micro-stepping.
Micro-stepping.
Yeah. The computer isn't trying to solve the entire flight path all at once. It solves for a tiny fraction of a second. The linear programming equation establishes a baseline fuel mass. It hands that data point to the differential equation.
Okay.
Then the calculus layer calculates the thrust-to-drag ratio for just, say, the next 10 milliseconds.
Oh, I see. And then it passes that millisecond of movement to the vector algebra to see how the trajectory shifted.
Yes. It's less of a straight line and more like the governor on a steam engine.
How so?
Well, as a steam engine spins faster, the mechanical governor expands, which automatically restricts the steam valve, which slows the engine down.
And that slowing down causes the governor to contract and open the valve again.
Exactly. It's a continuous self-correcting mechanical loop. In the aerospace MDO loop, the output of the vector trajectory feeds right back into the fuel optimization for the next 10 millisecond calculation.
And it just loops thousands of times a second.
Exactly.
That makes so much more sense. But, it's one thing to calculate thrust for a massive physical object you can clearly see, like a rocket.
Right.
It's entirely different when these exact same equations have to control invisible frequencies.
Yes, moving to the microscale.
Because the curriculum pivots here from massive rockets to the microscopic realm of electronics and digital signal processing. Specifically, it looks at a modern 5G transceiver.
And an electronic transceiver is just as complex and coupled as a launch vehicle. It's incredible. It requires the exact same three-stage mathematical engine to function.
Okay, so how does that map out?
Well, the linear algebra layer here is applied to the physical circuit board itself.
The document mentions using matrices to solve the mesh networks of the board traces, but, I mean, how does a physical copper wire translate into a matrix?
Well, think about a modern printed circuit board.
Hmm?
It has millions of microscopic copper pathways. They overlap, they branch out, and they all carry fluctuating voltages.
Right.
You cannot calculate the electrical current of one wire in isolation because the electromagnetic field of one trace affects the trace right next to it.
Oh, right, crosstalk.
Exactly, crosstalk. To understand the board, you have to write a massive system of simultaneous linear equations representing every single node.
And a matrix is just the best way to handle that.
Exactly. You arrange those equations into a giant matrix and solve the entire spatial state of the board's voltage all at once.
Okay, so the matrix maps the physical electrical state.
Yes.
Then calculus is applied to process the analog radio frequency waveforms. Because an RF wave isn't digital, right? It's not just a 1 or a 0.
No, it's a continuous physical wave of energy moving through the air, peaking and dipping.
Right, and calculus is the only mechanism that can measure that continuous, instantaneous rate of change as the wave actually strikes the transceiver's antenna.
Yes, the calculus tracks the kinematic movement of the waveform. But, and here's the issue, the waves that hits the antenna is never clean.
Never.
Which brings us back to the probability layer. Specifically, the use of Bayes' theorem to build digital signal processing filters, or DSPs. Yeah. Their job is to detect the true signal hidden inside atmospheric electromagnetic noise.
And the mechanism behind this is just fascinating to me.
Yeah.
Because when your phone receives a 5G signal, it isn't just cleanly receiving data from the cell tower.
Not at all.
It is getting slammed with background radiation from the sun, the magnetic field of a microwave oven in a nearby apartment, the chaotic bounce of the signal off a glass skyscraper. It is just a dense wall of static.
It is. And a DSP filter uses conditional probability to sort through that static. Conditional probability Bayes' theorem is a way of mathematically updating your belief about something based on new evidence.
You know, it's the exact same mechanism your brain uses when you are trying to hear a specific friend whispering to you in the middle of a crowded, roaring football stadium.
That is a perfect way to describe it.
Right. Your ear is physically receiving the chaotic roar of 50,000 people. It's just noise. But you have prior knowledge of what your friend's voice sounds like.
You know the baseline?
Exactly. You know their general pitch, their cadence. So as the sound hits your ear, your brain applies a probabilistic filter.
It ignores the outliers.
Yeah, it ignores the low rumbles and the high shrieks of the crowd, guessing in real time which specific frequencies most likely belong to your friend.
And that prior knowledge is the absolute key.
Yeah.
The 5G filter knows what a standard data packet should look like.
Okay.
So as the chaotic analog wave hits the antenna, the DSP applies a mathematical weight to the data. It literally asks, given the noisy spike I just received and my prior knowledge of the cell tower's frequency, what is the mathematical probability that this spike is the true signal versus just random atmospheric static?
Wow.
And it continuously filters out the low probability data, the crowd noise, leaving only the high probability whisper.
So the matrix maps the physical mesh of the circuit board, calculus measures the continuous invisible wave hitting it, and probability acts as the logic gate separating the signal from the noise.
Yes.
It is the exact same underlying architecture as the rocket, just applied to microscopic invisible frequencies.
It's the universal architecture of complex systems. But we have to admit, human engineers cannot solve matrices with millions of variables by hand.
Definitely not.
Or run differential feedback loops thousands of times a second with a pencil and paper. To actually execute this integration, we have to look at the foundational bedrock of all modern engineering, which is computing and software architecture.
Right. And the curriculum is very explicit here. It points out that software engineers are not writing raw mathematical loops from scratch every single time they build a system.
No. That would be incredibly inefficient.
Instead, they compile these unified concepts into massive object-oriented libraries, things like NumPy or SciPy in Python.
If we connect this to the bigger picture, software architecture is essentially the practice of packaging decades of dense mathematical theory into clean, accessible APIs.
Making it usable for everyone else.
Exactly. The curriculum maps out how specific math concepts are foundational to everyday software functions. For instance, function invertibility.
Right, from days 3 and 4.
Yeah, that is the core mechanism behind data serialization.
And for those listening, serialization is when a program takes a complex 3D object from memory, say in a game, and flattens it into a 1D string of text so it can be saved to a hard drive or sent over a network.
Right. And function invertibility ensures that this process is a perfect two-way street.
It has to be perfect.
It does. If the mathematical function used to compress the data isn't strictly invertible, meaning every single output maps perfectly back to one specific input, the data will corrupt when you try to unpack it on the other side.
The math literally guarantees the integrity of the data transmission.
Yes.
And then, when it comes to finding that data later, the architecture relies on monotonic intervals for search optimization.
From day 17.
Yeah, and I want to focus on the mechanics of that because it's brilliant.
It really is elegant.
If you have a massive database of 1 billion unsorted numbers, and you need to find the number 7, the computer technically has to look at every single entry until it finds it, right?
Right, a linear search, which takes massive processing power.
But a monotonic interval is a dataset that only goes in one direction. It is strictly increasing or strictly decreasing. It's already sorted.
And because it is strictly increasing, the software can utilize a binary search. It doesn't check every number.
It just jumps to the middle.
Exactly. It jumps to the absolute middle of the database. If the middle number is 50 and you are looking for 7, the computer instantly knows it can entirely ignore the upper half of the database.
It just throws out half the work immediately.
It cuts the workload in half with every single step. The mathematical property of the monotonic interval is what allows the search algorithm to be so unbelievably fast.
Here's where it gets really interesting, though. We see linear algebra pop up again here, specifically matrix inversions.
Ah, yes, day 11.
Right. And those are executed constantly for 3D graphics rendering. When a developer types a simple command to, rotate a camera in a digital environment, the computer is rapidly inverting matrices to recalculate the light and spatial projections onto your 2D monitor.
But the developer typing that single line of code doesn't need to know how to invert the matrix by hand.
Not at all.
They are utilizing a unified engine that has been neatly boxed up for them. And that realization that modern coding is the encapsulation of complex math into functional, easy-to-use tools is the entire point of the Day 23 curriculum.
It really pulls it all together.
It does.
Huh.
The document shifts from theory to a highly specific practical task for the student.
Yeah, the master schedule gives a very clear directive. It says, compile your local code snippets into a clean, standalone computational math handbook.
Which is a huge step up.
It is, because up until this point, the student has been treating their math like isolated textbook chapters.
Sure.
Just writing little scripts in a Jupyter notebook just to prove they understand the daily concept, and then moving on.
But the task for Day 33 provides a Python blueprint that requires them to fundamentally change the architecture of their work.
They have to build something real.
Exactly. They are instructed to use object-oriented programming to wrap all these core engines. The vectors, the matrices, the calculus solvers, the probability filters into a single, reusable class called an engineering math toolkit.
This is where the paradigm shift we talked about is fully realized. By forcing the student to write an object-oriented class, they are no longer just a student solving an equation for a grade.
They are encapsulating the math.
Right, they are building the tool.
They are acting as the software architect. They are taking the isolated boundary conditions we discussed and structurally hard-coding them into a unified Python library.
So next month, when they face a new engineering problem, they won't have to rewrite a differential equation solver from scratch.
No, they will just import their own toolkit and deploy the unified engine they built themselves.
That is so empowering. And the curriculum wraps up by stating that by structuring their code this way, the student is now structurally ready for advanced topics, things like applied engineering thermodynamics, fluid mechanics, and advanced algorithmic design.
Which makes sense because you cannot tackle fluid dynamics, which is, the chaotic nonlinear flow of liquids and gases, without having that unified engine of spatial matrices, kinematic calculus, and probabilistic error correction already humming under the hood.
You have to trust your tools before you can build the machine.
Exactly.
If there is a massive takeaway from this toolkit integration for you listening today, it is that knowledge, much like a mathematical formula, is practically useless when kept in isolation.
It really is.
True power in engineering, and honestly in complex problem solving generally, comes from the pipeline. It happens when you allow the output of one rigid system to become the input boundary condition for the next, creating a continuous feedback loop.
And it's the human ability to architect these object-oriented toolkits that allowed us to launch rockets and build global communication networks in the first place.
Absolutely.
But looking at this 33-day human curriculum,
Yeah.
it raises a really profound question about where engineering is heading next.
Oh, how so?
Well, we have spent this deep dive exploring how the human brain deliberately unifies these three specific layers, algebra, calculus, and probability, to parse reality.
Right, our three-layer engine.
But as artificial intelligence moves beyond just generating text to actually architecting its own structural code, you will inevitably begin building its own integrated mathematical toolkits.
Oh, wow. That is a fascinating pivot because we spent 33 days learning how to carefully integrate these specific systems so human engineers can understand and verify them. But an AI might not be constrained by our tidy three-layer architecture. It could combine variables, dimensional matrices, and probabilistic weights in frameworks the human brain hasn't even conceptualized yet.
It might just invent layer 4.
Layer 4, that's slightly terrifying, but also incredible.
Right. If the unified toolkits we discussed today are the foundational engines of the modern world, the structural toolkits and AI compiles tomorrow could solve engineering problems we don't even know how to articulate yet.
That is definitely something to think about. Thank you for joining us on this deep dive into the architecture of modern problem solving. Until next time, keep connecting those boundary conditions.